Hello friends, I'm going to talk about application of virtual world to problems of bending. So we take a beam of length L, we take two nodes 1 and 2. At node 1 vertical displacement is V1 and rotation of cross section about Z axis is theta 1. Similarly, V2 and theta 2 are vertical displacement and rotation of cross section about Z axis is theta 2. Now Y axis is pointing upwards. So vertical displacement is positive when it is upwards. Z axis is pointing towards us. It's a right-handed coordinate system. So rotation theta is positive when it is counterclockwise. We are assuming that shear strain gamma xy is equal to 0. That is, cross-sectional planes remain perpendicular to neutral surface after bending. Also, we are assuming a constant cross-sectional area of the beam. That is, cross-sectional area doesn't change with position along x-axis. Now, degrees of freedom at each node are vertical displacement of neutral surface and rotation about neutral axis. Neutral axis is z-axis. Now we have got four variables: v1 theta 1, v2 theta 2, to describe vertical displacement of the neutral surface. The vertical displacement can be described as a cubic polynomial, since we can use 4 degrees of freedom. So we can describe a cubic polynomial for the vertical displacement. So we can write vertical displacement V as n1 v1 plus n2 theta 1 plus n3 v2 plus n4 theta 2. Here n's are shape functions, or you can call them as an interpolation function or a polynomial. So I will explain first how to find n1. For finding n1, we use boundary conditions. V1 value of vertical displacement at node 1 is equal to 1. Rotation theta 1 is equal to 0. V2 is equal to 0 and theta 2 is equal to 0. So this is how neutral surface looks after deflection. So you see here slope is 0 and this vertical displacement is 1. Here our slope is 0 and vertical displacement is also 0. So we want to find a function that represents this curve. So we call that function as n1. Now we assume that n1 is equal to 1 plus ax plus bx square plus cx cube. You see we have got this information about this function. That is, this function has value 1 at x equal to 0. It has slope equal to 0 at x equal to 0. That is slope of function n1 is equal to 0 at x equal to 0. You see here we have got v is equal to this Since all theta 2, V2, theta 2 are 0, and V1 is equal to 1, our vertical displacement is same as N1. So we will put all these conditions on this vertical displacement N1. So our slope from this equation becomes A plus 2bx plus 3cx squared. Now our boundary conditions are at x is equal to 0, displacement is equal to 0, and theta is equal to 0. Putting that displacement is equal to 0, if we put x is equal to 0, sorry, here vertical displacement is 1, not 0. So at x is equal to 0, we get n1 is equal to 1, v is equal to n1. So this v is equal to 1 is satisfied. Now we take slope. It is 0 at x equal to 0. So we put x equal to 0. So a should be 0 for this condition to be satisfied. So our a is 0. At x is equal to L, vertical displacement is 0 and theta is equal to 0. So vertical displacement is equal to 0 gives 1 plus, this is already 0, b L square plus c L cube is equal to 0. And this slope gives 2bl plus 3cl square is equal to 0. Now we solve these two equations. For we have got two unknowns b and c, and we solve them. You see this gives 2b is equal to minus 3cl, b is equal to this. Substituting b here in this equation, we get c is equal to 2 by l cube and b is equal to minus 3 by l square. So our n1 is equal to this. Once we know n1, we can find its first derivative and second derivative. Similarly, we can find n2, n3, and n4. So what is the meaning of n2? So this is our initial line, initial position of the central surface, and so you see here our v1 is equal to 0, theta 1 is equal to 1. Our v2 is equal to 0, theta 2 is equal to 1. So we can find a function that will be called n2 which satisfies these conditions. We will follow the same procedure as done here. Okay, we start with this equation and we say that, okay, we cannot start with this equation. We'll have to start with a general equation. N2 is equal to a plus bx plus cx square plus dx cube. Then we will say that v is equal to n2. So we put x is equal to 0 and we get a should be equal to 0. Then we put dn2 by dx is equal to b plus 2cx plus 3dx square. Now at x is equal to 0, theta 1 is equal to 1 implies b is equal to 1. Similarly, we have to solve c and d. Now what is n3? So for n3, what we are having is v1 is equal to 0, theta 1 is equal to 0, v2 is equal to 1, theta 2 is equal to 0. How it will look? So this is the way N3 will look. How will N4 look? V1 is equal to 0, theta 1 is equal to 0, V2 is equal to 0, theta 2 is equal to 1. So that will look like, okay, so this is the way it will look like. Slope is 1. Our counterclockwise theta is positive. So our slope is 1 and vertical displacement is 0. Then here it is 0 and this. So this will be our N4. You see N4 is given as N4 is given minus x square by L plus x cube by L square. If we find its derivative, it is equal to minus 2x by L plus 3x square by L square. So at x is equal to L, we get it is equal to 1. And here we put x is equal to L. Our N4 is 0. Our V is 0. What is our V? V is equal to N4. So V will be 0 at x is equal to L. But our theta will be 1 at x is equal to L. So you see that this function represents shape function 4. So we can try to plot it. You try to plot it, see how it looks. So it should look something like this. This is the way only it can look. I don't see any other way it should look. So here the slope is 1. So our N4 is equal to minus x square by L plus x cube by L square. So you need to plot it and see how it looks. Use some mathematical tools to plot it and let me know what results you get. Now you see here, I have shown a beam and with nodal displacement V and theta, and also have shown vertical force applied on node 1. So as you see, it is positive when it is up in the upward y direction. And external movement F1, you see it is again positive when it is counterclockwise. Similarly, external force F2 and M2 are applied at node 2. So what are our unknowns when we solve this kind of a problem? There are some external loads, some concentrated load or distributed load on the beam. So either we have to find V vertical displacement node 1 or force. Similarly, theta 1 or F1. Or sorry, this should be M1. Okay. So similarly for node 2, it is F2 or V2 or M2 or theta 2. So these are our applied loads, distributed load, Newton per meter, point load newtons. Now we consider a virtual displacement field. So these V1, theta 1, V2, theta 2 are actual displacement field, actual nodal displacement variables. And they will define a vertical displacement field for this beam using the shape functions we described earlier. V is equal to N1 V1 plus N2 V2 plus N3 V3 plus, sorry, V is equal to N1 V1 plus N2 theta 1 plus N3 V2 plus N4 theta 2. Now you see, we consider a virtual displacement field given by delta V1, delta theta 1, delta V2, delta theta 2 is equal to 1, 0, 0, 0. So delta V1 is 1, delta theta 1 is 0, delta V2 is 0, delta theta 2 is 0. So this is our virtual displacement field. So our virtual displacement field becomes N1. Okay. So what is external virtual work? So you see this virtual displacement is 1 here for node 1. So force F1 will do 1, F1 into virtual displacement 1. Now virtual displacement of node 2 vertical direction is 0, so F2 will not do any work. Similarly, M2 will not do any work. Similarly, M1 will not do any work. So external virtual work done during this virtual displacement is given by F1. Now you see here, look at this. So this is a vertical displacement and this is rotation of a plane. Similarly here, this is our initial plane which is perpendicular to the cross section. And this is initial position of that plane, this is the final position of the plane as the beam deflects. So you see rotation here is theta clockwise. Here rotation is counterclockwise theta. This theta is positive, this theta is negative because clockwise rotation is considered negative here. Now what is the displacement of a point on the cross section? Initially cross section was like this, finally cross section is perpendicular to the band neutral surface. So we will see that this cross, any point on the cross section moves in the horizontal direction by this displacement. So if we look at my whiteboard, so this was my initial position of the neutral surface, and my cross sectional plane was like this. Now after rotation, this cross sectional surface or plane looks like this. The point which was here has moved to this position. So this is our displacement. You see our x direction is this. So displacement is in negative x direction. You see this rotation is positive theta. So our displacement becomes, this position is y. So we say u is equal to minus theta y. If this is a small rotation, we can say this displacement u, which is in x direction, and it is in negative x direction. This magnitude is theta into y. Similarly, same thing like s is equal to r theta, where s is the arc length, theta is the radian is the angle in radians, r is the radial distance. Like this is s, this is r, this is theta. Same way we are getting our u is equal to theta into y. Since with counterclockwise rotation, it is going in negative x direction, u is equal to minus theta. So your beam is like this. So initially, which the plane that was like this, now it rotates. It stays perpendicular to the neutral surface. Initially, neutral surface was flat, so our cross-sectional plane was perpendicular like this. Now, since this surface has rotated, you see it has rotated. So plane has also cross-sectional plane has also rotated from its initial position, which was like this. Now, if you see here, so rotation is like this. Initial plane was like this. So our rotation is clockwise here. So what is our displacement? It goes in positive x direction. So our displacement becomes u is equal to theta y. Since theta is positive, is negative, so we put a minus sign to get a positive value of the horizontal displacement. So you see here this expression is valid whether theta is positive or theta is negative. This theta we can say is the slope of the deflection curve dv by dx. So here your slope of the deflection curve is positive. Here your slope of the deflection curve is negative. So what is our strain in x direction? Epsilon x is normal strain. It is given by derivative of it is given by dy dx. So this is nothing but minus y d square v by dx square. So stress sigma xx becomes you multiply by Young's modulus. So we get this expression. Second derivative of vertical displacement is given by this expression. We had earlier seen that vertical displacement is nothing but n1 v1 plus n2 theta 1 plus n3 v2 plus n4 theta 2. So it's second. These are nodal variables, so which are not changing with x. So you have to only differentiate the shape functions. We can put back the values of these derivatives. So we get stress as this. Now what is the virtual strain? Virtual strain is given by derivative of virtual displacement. What is our virtual displacement? Some from here. So minus y virtual rotation. So minus y. What is our virtual rotation? Derivative with x of virtual displacement. And virtual displacement is n1 for the assumed virtual displacement field here. So virtual strain becomes derivative with x of minus y into dn1 by dx. This delta v1 is n1. So this is equal to, now y is an independent variable. So it's a coordinate, vertical coordinate. So it is treated as a constant. So you're adding minus y into second derivative of n1 with x. So we just put the value of second derivative of n1 with x. This is this. Internal virtual work is given by actual stress into virtual strain integrated over the volume. So we have taken first term of the sigma xx, this term, and entire virtual strain. So we do this integration and we get this expression for internal virtual work. So you see this expression is getting multiplied with with V1. Okay, that is the displacement of vertical displacement of node 1. That is the only term that will get multiplied. So this is a constant. This thing has been integrated along with this multiplication. Next time we will do take this product of this and this virtual strain and integrate. So that term will be multiplied by theta 1. Similarly, other terms. If you see here, this is a repeat of the previous slide. You see virtual work and bending. Internal virtual work is equal to external virtual work. Gives these equations. So this is my stiffness matrix. This is my force vector. So these are my, sorry, this is my displacement field vector. This is my force vector. Force vector has static sign convention of forces and moments. That is counterclockwise movement is positive and upward force is positive. So these are the terms that are coming after integration. First row is generated. Other three terms of sigma xx, they are the remaining terms of first row of stiffness matrix, as I explained earlier. Second row is generated by virtual displacement field given by this. And we get external virtual work as M1. Similarly, third row is given by this, fourth row is given by this. So we have got right hand side vectors as well as stiffness matrix. So now we do an example. You see there is a beam of, this is a cantilever. Node 1 is fixed. So our vertical displacement as well as rotation are 0 here. Force P is applied at this far end. So there is no rotation applied at far end. So our force, vertical force F2 is equal to minus P as it is downwards. And rotation and movement here is 0. M2 is 0. Now in that stiffness matrix, since we are having V1 and theta 1 as 0, we eliminate first two rows and first two columns. So we are left with this set of equations. So we can solve it and get our V2 and theta 2. So this is as expected. This is our vertical displacement. Here it is negative because our positive direction is upwards. Similarly, theta 2, you see as it rotates, your theta 2 will be clockwise. So it should be negative. So both V and theta are negative at node 2. Now we can do another example where we applied load in the middle. This is a simply supported beam. Our boundary conditions at x equal to 0 are displacement, vertical displacement is 0, and bending and external movement is 0. Similarly, at node 2, our vertical displacement is 0, and also external moment is same. So this is here. You see, this is our simply supported beam with load applied in the middle. If we apply a virtual, now we are having no force at, no external force at node 1 and node 2. Okay. So we want to find the force vector. So how do we find the force vector? We first assume a virtual displacement like this. So what is external virtual work? Whatever is the burden by the forces applied on this beam. So that is F1 into 1. Whatever is the external force here, because of the support, there is a force coming. F1 into 1 and into force P multiplied by the virtual displacement at this middle position. Since both of them are in opposite direction, P is downwards, so there has to be a minus sign. P into virtual displacement at x equal to 2. What is virtual displacement at x equal to 2? We have to find the value of n1 at x is equal to L by 2. You look here, n1 is given by this expression. Put x is equal to L by 2. What do you get? Here it is L by 2, it's going to become 1 by 4. And again, this is L by 2, this becomes 3 by 4. 1 by 4, 3 by 4. So it becomes minus half. So we get value of half. So we get F1 minus P by 2. So delta V is equal to this, as I have shown here. At x is equal to L by 2, delta V is equal to half. For virtual displacement, this delta V is equal to N2. At x equal to L by 2, your delta V is L by 8. So external virtual work becomes M1 minus PL by 8. You see P into delta V at x equal to L by 2, which is L by 8. For virtual displacement field 0010, virtual displacement at x equal to L, virtual displacement is given by this, at x equal to L by 2, this will be this half. Similarly for this case, at x equal to L by 2, virtual displacement is minus L by 8, so external virtual work is this. So equations of equilibrium are given by this. These are our original stiffness matrix, but our force vector has changed in this case to this. Eliminating first and third row, since we know V1 and V2, which are 0. We are left with this equation. So solving theta 1 and theta 2. Similarly, we can also solve for the unknown forces F1 and F2. M1 and M2 are 0 here because external supports are not providing any movement. They are only providing a vertical force. So we get the value of F1 and F2 as P by 2, which is what was expected. Thank you.